Hello scholars and welcome back to Mr. Sniffin's geometry class. Today we will be talking about angles. Angles, as we mentioned previously, is basically the shape that gets formed, or that wedge type of shape that gets made whenever two lines intersect, or two rays, or two segments, any combination thereof, but that little pocket corner that gets formed. In terms of an angle itself, there is no actual way of numerizing it. It's kind of a shape itself. It's like assigning a value to a square or to an octagon. We can only describe its shape, but we can't necessarily count it until we start using different types of methodologies. There's three different popular methodologies that are used, and they kind of have different values in different types of field of study. The most popular is degrees, which we're going to be working with today, but the other two you have are radians, which relate to the number of radiuses that go around a circle, and it's dominant within the field of mathematics because it allows for you to work with this number pi when doing types of circle equations and things like that. The other methodology is gradients or gradients, as some say. It's basically a system of measurement that's devised around the 90-degree angle measure, or basically like the quarter of a circle, and it's typically used within engineering fields, but it's not too common in many others. The most common, though, and the one that relates to the vast majority of society, is going to be what you would call degrees. Degrees themselves are the numerical symbol or the methodology used to divide a circle up into the number 360, and that little wedge that gets divided by forming radiuses outward becomes your degree measure. Degrees themselves have a long history dating back to the Babylonian eras, as we've talked about previously in our geometry history lesson. There is some variability in terms of its history, though, in terms of its usefulness. Babylonians themselves are theorized to have used this number 360 based on the fact that they have a 60-digit number system. It also has relations to hexagonal geometry as well. The Egyptians also used the 360-degree method, or degree symbol. They're actually quoted or shown within archaeological research to be the first ones to use that circular degree symbol. Their documentation shows how it's been related to being able to cut a circle up into 6 different perfectly shaped triangles, and taking that 60-digit number system that the Babylonians used, multiplied it by those nice 6 triangles, and then you get 360 as well. So there is some variability in terms of its history. There's also notions of Ptolemy doing it with the sine method as well. But for today, we're talking about just how we go about finding angles in common geometric shapes like lines, triangles, and quadrilaterals. So let's take a look at our notes for today. Make sure, please, got your title along the top, angle measures, and we're looking at around July 22nd, one pages. And our final solution for today, our final notes, are going to look a little bit something like this. We're just going to have 4 different diagram examples and just some data associated with them. So let's get started. In our first example here, we have what we can call line AC, line AB, or if we had, like from yesterday, some type of lowercase letter, we can say line L. What we're going to be looking at today is how we go about quantifying some of these different figures with degrees, though. This first one here, this long line on the bottom, which we can call angle ACB, is actually equal to or equivalent to 180 degrees. What you'll notice on your paper, or on my paper here, is that we have this M symbol right before our angles. At the end of yesterday's lesson, we talked about congruency, which was talking about how two shapes might look identical. Today we're using the equal sign to talk about the actual numerical amount, because we're using that value of degrees. Any type of line, any line at all that we have like for instance Rx here on the bottom, is always going to be equivalent to 180. It's essentially how you would draw like a diameter across the circle. If a circle is 360 and we cut it in half, we got 180. One thing that you can also talk about is that all the angles that get formed as we go about forming that line, all the angles that share the same vertex, once added together will also be equivalent to 180. So if we take in this shaded angle here and this large obtuse angle here, combining them, adding them, finding our sum, we get 180 degrees. Next we have triangles. Triangles themselves are also equivalent to 180 degrees. You might think while looking at this what we call triangle symbol RSX, and your orientation doesn't matter. You can call it triangle XSR. You can do it however you want. But triangle RSS is going to be equal to 180 degrees, meaning if we add all three angles together, we end up getting 180 degrees as well, which we can notate as such. And you'll notice in this particular example, I'm only using individual letters to talk about each particular angle because we can kind of assume just through common sense that the measure of angle S is referring to the S over here, whereas along the top, in this particular example, we had shared vertices, so we needed to kind of differentiate with those three-letter notations. But let's take a look here. If we were to go ahead and start to pull apart, say, a triangle, and needed to solve for missing angles that might be there, we can use an example like this along the bottom left here. Here we have what we would call as triangle GHJ. We can go about labeling some of our angles down here. So let's just start. We're going to say the measure of angle H is our unknown, right? This is the only one we haven't been told. We know that the measure of angle G is equal to 60. And the measure of angle J is equal to 40. If we want to go ahead and find that missing value, knowing that all three angles, once combined, equal 180, we're going to set up an equation where we're just going to add everything together. So we could say that x plus 60 plus 40 is equal to that total of 180 degrees. And now we just go ahead and basically solve everything out. Combining all of our like terms, subtracting, and getting a remainder of 80 degrees. One thing to note here, this angle along the top, which we're going to describe as 80, not in every diagram that you're going to see or just type a question to try and generate that geometric reasoning we're doing this summer, is actually going to be accurately drawn. I just arbitrarily place these numbers down on this particular paper, so you're going to have to work with it in that way. One cool thing I want to show you here is what's called the exterior angle theorem. I'm going to pop up a definition for you in a moment, but you might remember from class this theory, and it was hard for me to wrap my head around it at first, but I think it's really cool. The exterior angle theory is based on this notion of a line. Along the top here, we said that ACB, or line L, is equal to 180 degrees. Therefore, we know that this whole shaded area right here is equivalent to 180. What our exterior angle theorem says, or what we would describe as like a postulate, is this empty space right here is equivalent to our two non-adjacent angles, meaning that angle SGH or SGH, is equal to, in measure, angle H plus the measure of angle J. To go about and verify this, we know that angle H was equal to 80, correct? And angle J was equal to 40. If we wanted to do an equation and solve for this missing angle just on this diagram here, kind of like we did on the top, we could say that the measure of angle SGH plus the measure of angle HGJ is equal to 180. We actually went ahead and filled everything in. We have 60 plus our unknown is equal to 180. And if we minus 60 minus 60, we get 120 equal to our unknown over here. If we just add it, H and J, 80 plus 40, we'd also get 120. So these are kind of these cool little rules that we can build up over time, but they all work on that binomial rationale that we described earlier throughout the week and last week. All these fundamental principles continuously add up. The last piece I want to check in with you today along the bottom is going to be with a quadrilateral. We can just simply say that all quadrilaterals, which means all four-sided figures, because we got that Latin QUAD, stands for fort. Laterals meaning sides, so four-sided figures, equal 360 degrees. That means if we were to add all these angles up, like x plus y plus a plus z, we'd end up getting 360 degrees. So this is just a basic representation. As remember, this is our summer class, so we're going through some of this stuff quickly. If you do have more questions on this, you can look through our YouTube channel. I've already have 35 videos that have gone over a bunch of different stuff. If you wanted to see other representations of this with me doing it, feel free to look at the final review, which has some examples, particularly of the triangle setup there. For your lesson today, after the video on Delta Math, you're going to be practicing some triangle equations with the interior being 180 and that exterior idea of those non-adjacent angles. If you have any questions about today's video, I know go through it quickly, please jump into office hours today. Be more than happy to help answer anything, catch you up, anything like that. Also, if you're just looking for different YouTube examples, for instance, you can just search for triangle sum theory would be one of the terms that you'd use for finding triangle help, or quadrilateral sum theory, which talks about adding all those angles as well. Tomorrow we're going to be talking about parallelograms and kind of special quadrilaterals and how these rules from today can relate to some other topics as well. But if you have any questions, feel free to drop on by. And as always, have a nice day. Stay safe. Email me if you got any questions. All right. Bye.